Hey, welcome everyone to this week's CDAC webinar. Today, we're delighted to introduce our colleague, Brian Maple from the Department of Physics at the University of California at San Diego. Brian holds the position of Distinguished Professor of Physics, the Bernd Matthias Chair, and is the chair of the Physics Department at UCSD. Brian is well known to many of you as one of the leading experimentalists in the study of strongly correlated phenomena in D and F electron materials, and has made many contributions to our understanding over the years in superconductivity, magnetism, heavy fermions, and non-Fermi liquid behavior. And that includes exploring these phenomena in extreme conditions such as high pressure and high magnetic fields. And for all of this, he's received many honors and awards, including election to the National Academy of Sciences in 2004. Brian has been very active also in the NNSA community, having trained a number of students and postdocs who now have positions in the labs, as well as training many in academia. So we're particularly delighted, Brian, that you're able to give a talk today. We're looking forward to your presentation on uranium ruthenium silicon.
Thank you, Russ. I'm very pleased to be able to do this. I am having one technical problem. The meeting is being recorded, and that's right in the middle of my screen, and I can't seem to get rid of it. So I'm sorry about that. I don't know what to do about that.
I think
if
you click accept, or
well, there's two
yeah,
things.
and we can't see it.
Okay, but the trouble is I can't see the middle of my screen.
I think you can just click on any button.
Yeah, tell it accept.
Yeah.
Okay, there's one that says leave meeting and the other says continue. Which one?
Continue.
Okay, okay, you're right. Thank you. Okay.
Great.
All right, and I can't see anybody either, but somehow we'll get through this. Okay, so anyway, I'm really pleased to be able to do this. I'm sorry about these technical problems. As the title indicates, I want to talk about novel electronic phases and competing interactions in the correlated F electron compound uranium ruthenium 2 silicon 2, which I've studied for a long time, many years. Okay, now I'm having trouble advancing the screen. Okay, I'm sorry. Oh, there we go. Okay. And I can't read the top. Well, anyway, I'll try to struggle through these difficulties. Anyway, there's been an enormous amount of interest in this compound during the past 3 decades, and there have been over 1,000 papers written on this subject. And fortunately, there are some very nice reviews, which I've indicated in the top by Maidosh, Openeer, and Riceborough. Basically, in this material, there's a delicate interplay between competing interactions, leading to a wide variety of correlated electron phases and phenomena. So one finds this elusive hidden order phase whose order parameter has not yet been identified after more than 3 decades of research: unconventional superconductivity, ferromagnetism, antiferromagnetism, spin density wave order, quantum criticality, and non-Fermi liquid behavior, as you'll see later, and other novel electronic phases. It turns out that these interactions can be tuned via chemical substituent composition, which I'll call X, pressure, and magnetic field. And you find these very complex temperature versus X, P, and H phase diagrams. So I kind of look at this compound as a platform for studies of emergent phases and quantum criticality. So as a little bit of background, we've been doing exploratory experiments, and many people have, involving the substitution of transition metal elements for ruthenium in uranium ruthenium 2 silicon 2. And today I want to concentrate on the effect of isoelectronic substitutions of iron and osmium, because they're similar to the application of pressure in driving a transition from the hidden order phase to a large moment antiferromagnetic phase. And both hidden order and this large moment antiferromagnetic phase then can be accessed at ambient pressure through these substitutions of iron and osmium. So one advantage of this, apart from the fact that you do introduce chemical disorder or atomic disorder, is that experimental techniques that are not readily applicable to study hidden order and large moment antiferromagnetism at high pressure, such as ARPES, SDM, inelastic neutron scattering, high magnetic field studies, and so on, these can be employed at ambient pressure through these substitutions in single crystal materials. And hopefully these experiments will eventually yield some clues about the identity of this hidden order phase. So in this talk, I want to give you some examples of experiments, mostly on single crystals for iron and osmium substitutions carried out in our lab and labs of collaborators. But first, I want to give a little bit of background to uranium, ruthenium, 2 silicon, and this hidden order problem. So uranium, ruthenium, 2 silicon 2 is a heavy fermion F electron compound. Effective mass is about 25 times the free electron mass. Hidden order phase occurs below 17.5 Kelvin. As I said, the order parameter has eluded identification for now more than 3 decades. It exhibits unconventional superconductivity, which appears to be D-wave superconductivity. It has both point and line nodes on the Fermi surface and 2 energy gaps. I'll show you this in a moment. And then the competing interactions, of course, give rise to these complex phase diagrams. So this is a plot of C over T versus T squared, actually from our work back in 1986. And there were 3 papers originally published by Schlabitz, who discovered this material, and then Polstra, John Maidash's group, who did beautiful work on single crystals, and this work that I'm showing you right here. So what you find is that if you look above, in the state above the temperature below which you get this hidden order phase, C over T versus T squared, you can describe it as a straight line. You can extrapolate it back to T equals 0 and deduce the electronic specific heat coefficient that it would have if it didn't undergo this ordering. And then you construct a parallel line, which would represent the same Debye temperature that connects to the curve here. And then if you just trace this to 0 temperature, this is the gamma that you would get below this formation of this phase. And this little jump here is due to the superconductivity. And so this represents a reduction of the Fermi surface by about 40%, over which presumably a gap forms due to this hidden order phase. And by looking at this exponential part in the electronic contribution to the specific heat, you can deduce or estimate that the gap's about 130 Kelvin. So here you see onset of superconductivity around 1.5 Kelvin. This is a broad transition. This is a polycrystalline material. And then this is the part of the upper critical field curve right here. And here's some of the really nice data on the single crystals from Polstra and co-workers. There's a resistivity versus temperature. So if you, this is along the C-axis and in the basal plane. And then you see for this curve, you get increase of resistivity, condo-like scattering, rolls over and goes into coherent, approaches a coherent ground state. And then at a certain point, you see the formation of this hidden order phase in these features here, which are shown at in the lower part of the figure in more detail. And then you see the drop in resistivity due to the superconductivity. Here you see the magnetic susceptibility along the easy axis and the hard axis. And at high temperatures, you get Curie-Weiss behavior with the effective moment close to the free ion value. Then it rolls over, and again, you see a little kink due to the hidden order. And early elastic neutron scattering measurements were made. Neutron diffraction measurements were made by Colin Broholm and co-workers. And it's what they saw was an antiferromagnetic structure shown here. And however, the moment was only about a few hundredths of a Bohr magneton. And without going into a lot of details, it's widely believed that internal strains quench in a small concentration of this large moment antiferromagnetic phase, and that's really is what is ordering here. And the hidden order phase doesn't appear to have any magnetism associated with it. Here are some measurements and some more neutron diffraction measurements made under pressure by Nick Butch and co-workers. Nick is one of my former students. He's done a lot of beautiful other things recently in addition. And this is a single crystal with a residual resistance ratio of about 22.5. The pressure transmitting medium is helium. It's the most hydrostatic one available. And basically what you find is a first order, hidden order to large moment antiferromagnetic transition along this line here, which we call a T sub X. So you can see the magnetization jumps up very sharply when you get into this magnetically ordered phase. And so the phase diagram then has a hidden order region, a superconducting region here, and then the large moment antiferromagnetism. This is a line of first order transitions. And these points are due to a number of other previous investigations which really discovered basically the components of this phase diagram, but the pressure transmitting media gave rise to strains that we believe don't represent the actual pressure where this is supposed to occur. But basically, it's the same phase diagram. So I don't want to make this seem like we were the first to do this. We were not. And in fact, the previous papers are listed here. But I think the data that I just showed you probably represents the best disposition of this phase diagram with respect to pressure. Okay, so what do we know? Hidden order has an energy gap of about 130 Kelvin. It has itinerant character. I think you would infer that from the partial gapping scenario. It also has to have local character. These phenomena are, driven by hybridization between the localized 5F and conduction electron states. The small moment antiferromagnetic phase resides within the hidden order phase, but that really seems to be a parasitic phase. It's extrinsic and due to these small strains that quench in the large moment antiferromagnetic phase throughout a small region of the volume. And then other measurements, also early measurements show that there's an energy gap where it's been observed in all these experiments we mentioned here, and also in various spectroscopic measurements, infrared tunneling, spin excitation spectra from inelastic neutron scattering and STM and so on. Okay, so a little bit more. From inelastic neutron scattering, there are basically two distinct modes with energy gaps in the hidden order phase that emerge out of longitudinal spin fluctuations at high temperatures. And so one of them is a commensurate mode with this wave vector and a gap of about 2 millielectron volts. And then there's an incommensurate mode, Q1, with an energy gap of about 4.5 millielectron volts. Okay, and then from Shubnikov-de Haas measurements, one finds that the hidden order and large moment antiferromagnetic phases have similar electronic structures. So there are only small changes in the SDH frequencies and nearly a continuous effective mass as you go through the hidden order large moment antiferromagnetic phase boundary under pressure. And this suggests that you are doubling the lattice constant along the C-axis or downfolding in Q space in the hidden order phase. So that one feature that is suggested by these measurements. Okay, so a lot of ARPES has been done on the hidden order phase, and there one finds a restructuring of the Fermi surface at certain regions of the 3D Brillouin zone boundary, leading to this partial gapping of the Fermi surface. And then another interesting feature is what are referred to as Ising quasiparticles. There's anisotropy of the quasiparticle G factor, a huge anisotropy. And then also one of the more intriguing candidates for the hidden order phase is what's called a chirality density wave. And this comes from polarization resolved Raman spectroscopy measurements made by Kung and coworkers. And if I have time, I'll come back to that. But I'm not going as efficiently as I had intended, so I may not get there. Okay, so this is just quickly the inelastic neutron scattering measurements. So remember, there's a commensurate mode with a gap of about 2 MeV. It's located right here. So you see, here's the gap. And then the incommensurate mode at this wave vector with a gap of 4.5 MeV. And you see it here and here in these neutron scattering spectra. So the Q1 mode is related to strong Fermi surface nesting from gamma to Z in the BCT normal phase above the hidden order transition. So it's kind of related to the ordering. It goes away when you go into the ordered state. And then the Q1 mode remains inelastic in the large moment antiferromagnetic phase. And it's the basis of strong spin fluctuations above T0, and then the gapping of spin fluctuations occurs below T0, which according to Weeb in this original work results in the removal of entropy below T0, which occurs. And so they conclude that the hidden order transition seems to involve some rearrangement of the electrons at the Fermi surface. And although I won't really get to that part, a recent ARPES work done with Andre Santander-Sereau just came out in a PNAS, shows that the Fermi surface topology actually does not change when you go into the large moment antiferromagnetic phase, but there are portions of it that do change, throughout the change a small amount. Some features do not change as you go into the antiferromagnetic phase. So it seems to be very, very subtle. And this is the SDH measurements. So you see the amplitudes versus frequency. This is in the hidden large moment antiferromagnetic phase. This is in the hidden order phase. You see these features are very similar. And if you look at the frequencies as you go from the hidden order to the antiferromagnetic phase, you see that they don't change a lot for these different orbits as you go through this phase transition. And the effective mass actually goes through rather smoothly. So again, this suggests similar Fermi surfaces in the HO and large moment antiferromagnetic phases, and suggests lattice doubling in the large moment phase due to this ordering wave vector that we've been 001. This already occurs in the hidden order phase. So something in there is ordering so that the basically the lattice doubles in the direction of the C-axis. It's already doubled, let me say it that way, in the HO phase. Okay, and a few comments about the superconductivity. This is from the work of Kasahara and co-workers. It's based on thermal conductivity measurements as a function of field and temperature. So as you can see, there are line nodes on the Brillouin zone boundary on the spherical light hole-like Fermi surface. So these are the line nodes here and here. And then point nodes along the C-axis on both the spherical light hole-like Fermi surface and the elliptical heavy electron-like Fermi surface. And so you see these point nodes, these little dots here on both of these Fermi surfaces. And this is believed to be due to spin singlet pairing. And again, superconductivity with two distinct gaps having different nodal topology. And this has been suggested to be a candidate for a topological superconductor. It's a 3D chiral D Weil superconductivity, according to this work by Yanazawa. And there are some other more recent experiments that support this interpretation. All right. Now, there's been many attempts to describe what this hidden order is due to, what is its order parameter. And so I've just, I list, there's a lot of them here, probably not all of them, but maybe most of them. And you can see that there are many different types of phenomena associated that have been associated with the hidden order. And most of these are theoretical contributions. And then many of these models are based on localized F electrons. Those are the ones with the asterisks here. And then the other ones are take into account the itinerant nature, which of course I think is an important part of the problem as well. Okay, so let me now turn to the transition metal substitutions for ruthenium in uranium ruthenium 2 silicon 2. So anyway, these are manifested in different ways or give rise to different phenomena. So this is just a little figure here. So on this side, if you make these substitutions, you dope the material with holes. These substitutions dope it with electrons. These are isoelectronic substitutions, but one important thing is that when you substitute iron, it decreases the unit cell as you add more and more iron, the volume of the unit cell, whereas osmium increases the volume of the unit cell. So that will turn out to be important. And in this part, you find ferromagnetism in all these cases. This was done back in '89. And then in this case, there was a lot of work done on rhodium where you find antiferromagnetic behavior, and then some recent work we've done with cobalt and iridium also show that you get antiferromagnetic phases. Now, iron and osmium, which are isoelectronic, drive this material out of the hidden order phase into the large moment antiferromagnetic phase, and is very similar to the application of pressure. And this just shows where these substitutions are made. So here are two examples of some of the interesting phase diagrams that one finds. This is work with rhodium that a number of people have contributed to. So you have hidden order, antiferromagnetism. Down here, you would have superconductivity at much lower temperatures. And then nothing appears to happen over here. You get complex antiferromagnetic order. Again, kind of an open space here, so to speak. And then high temperature antiferromagnetism. And in this case, for rhenium substitutions, you both of these types of substitutions suppress the hidden order. And here, again, nothing appears to happen, but the other interpretation is that the transitions become broadened, and so maybe you just can't see them in this region. And thermal expansion measurements and specific heat measurements indicate that the gap is decreasing as you go along this line. Okay, then you enter into this ferromagnetic region, and some very interesting non-Fermi liquid type features appear in this region right here. And so we've done a lot of work on this, this phase diagram over the years. Okay, so now coming to the iron substitutions, which is where this more recent thing we've been working on started. This is we first did this in polycrystalline specimens, and then we changed to single crystals as we got more deeply into trying to understand what was going on. And this is a first paper in PNAS in 2016, where this was published. And this is just showing you what one of the single crystals looks like. It's grown in a tetrarch furnace by the Chirality method. So you have to, it takes a lot of time to grow these. So you can't grow a lot of specimens, but this is what we found for the single crystals. So this is the phase diagram. So this is temperature versus iron composition. So this is paramagnetic here, hidden order here, and this is a large moment antiferromagnetic phase. And then down here, if we were to try to investigate this region at much lower temperatures, you'd find superconductivity, but we don't really know at this point how it behaves. So we're concentrating on the hidden order phase. Okay, so you see then this is similar to the phase diagram that I showed you earlier under pressure. There are kinks in this phase boundary at here about 0.15 for X. When you go from the hidden order phase to the large moment antiferromagnetic phase along this phase boundary. And the pressure at which this occurs with the undoped sample is at 1.5 GPa. Okay, and so here one early interpretation we made was that this appears to be driven or could be driven by chemical pressure, because the reduction in the unit cell volume that would give rise to this phase diagram is similar to that which would occur under pressure. And so we thought that that was simply the reason that was driving it. I mean, pressure drives it. And so now we could assume that chemical pressure would basically do the same thing. Now, in retrospect, and I'll come to this at the end, there is a chemical pressure effect, of course, but really what appears to be driving it is that the hybridization of the iron D states with the uranium 5F states is much stronger than it is for ruthenium. So by replacing ruthenium with iron, you're increasing the hybridization, and that, after all, is what must really be driving the transition. And of course, the hybridization would increase under pressure. But anyway, in the beginning, this is what we assumed. But I think it's more complicated. I'll come back to that later. Here is the neutron diffraction, the magnetic moment versus temperature versus iron concentration from the work of Das and co-workers. And so these are basically the magnetic moment as a function of temperature as you lower the temperature for various compositions of iron. And so this is in the hidden order phase, this is in the antiferromagnetic phase. And if you look at the projections of the moments onto this plane here, at say 0 temperature, then this would be the moment versus iron concentration. So you see it increases in the hidden order phase, and then at about X equals 0.1, attains its largest value and then decreases thereafter. Okay. Now this is measured at low temperatures, and bear in mind that the transition at higher temperatures close to the phase boundary actually occurs out here. So that's why you might think there's a discrepancy between this hidden order transition a composition and the one that happens along the phase boundary, and it's just simply due to the fact that the line between the hidden order and antiferromagnetic phases is not vertical, it actually has a slope. Okay, and this just shows you the measurements upon which we base this phase diagram. So this is normalized resistivity versus temperature. And so you see features due to the hidden order transition down in here, the antiferromagnetic transition up here. These are just derivatives to accentuate the features. And you see similar things in the magnetization, in the susceptibility, if you like. And then this is just another way of representing the data where you can actually make these features look more like the specific heat, by making this kind of a derivative. And but anyway, you can see the transitions in all of these features. And then this is what happens to the specific heat divided by temperature versus temperature itself. So down here you see sharp hidden order transitions, then they get more broad when you get into the antiferromagnetic phase. But interestingly enough, the hidden order and large moment antiferromagnetic phases have similar transport and thermodynamic properties, although you do see differences, but they're similar. And anyway, the phase boundary still, there's still more work to be done to map it out in more detail. Okay, these are some thermal expansion measurements. And this is in the AV plane and along the C-axis. Again, you can see features due to the hidden order phase and the antiferromagnetic phase. This is the volume thermal expansion deduced from these data right here. And there are significantly larger jumps at the paramagnetic antiferromagnetic phase transition than at the paramagnetic hidden order phase transition in these data. You can see that here. And also there are some additional peaks that are kind of hard to pick out here, but they indicate the transition from the hidden order to the antiferromagnetic phase as you come down in temperature, because you first go from the paramagnetic to the hidden order phase. And then because this phase boundary is not vertical, you then go into the antiferromagnetic phase. So some of the complexity is due to that second transition. And if you take these data and calculate the pressure dependence of the hidden order transition using the Ehrenfest relation, then you get these black points right here. And then those can be compared with the actual measurements made in a piston cylinder cell, just detecting the hidden order. And those are the red points right here. So you can clearly, see this line that delineates these two phases from one another, makes this phase boundary. And you can also analyze these resistivity, specific heat, and thermal expansion curves. And so basically what we've done is to look at these parts below the transition, which have exponential contributions, which you can then fit to the data and estimate the gap associated with the formation of the hidden order phase. And so from the resistivity, as you increase the iron concentration, you see that the gap decreases and then jumps up and then decreases. And then similarly from the specific heat, you find a similar behavior. And then also from the volume thermal expansion, you also see a similar behavior. So, and then the scale here is basically very, very close. So this then is one feature that one piece of information then that characterizes the transition from the hidden order phase into the large moment antiferromagnetic phase. Okay, and then we've done work on the pressure dependence of the electrical resistivity for iron, and then recently work on osmium, which I'll come to towards the end. I was also recently published in PNAS. And so here basically what you find is that if you measure the resistivity under pressure in a piston cylinder cell, you can see distinct features due to the hidden order and the antiferromagnetic transitions shown here. And then if you take these temperatures and plot them versus pressure at various iron concentrations, then for the pure compound, you see this is the hidden order phase boundary. And then it's a little bit hard to see here, but there's a distinct kink as you go into the antiferromagnetic region. And then you can take this composition of iron is 0.025. And then you see that the kink occurs right here. And so you can extrapolate it down to the concentration pressure plane and find a point here. And do the same thing for successively higher iron concentrations. And then the projections then define this plane here, which is the region in composition versus pressure in that plane within which hidden order occurs. And then in this other region, you get large moment antiferromagnetism. So basically, this says that the tuning of the hidden order phase to drive it into the antiferromagnetic phase, either by pressure or by substitution of iron, these two contributions are additive. And so if you put a little bit of pressure on it, or if you put a little bit of iron in it, then you need less pressure to go through the transition. And so these two mechanisms are additive. Okay. All right. So now let me turn to some measurements in high magnetic fields. And so here, but before I do that, let me just say a little bit about quantum criticality. So temperature T versus control parameter, which could be, in our case, composition pressure or magnetic field phase diagram. If you consider this, then delta can tune a second order phase transition at zero temperature at a quantum critical point. And so basically what happens is that you find non-Fermi liquid behavior in the low temperature physical properties near the quantum critical point. And then often you find a dome of superconductivity, or it can even be an exotic magnetic phase that sometimes envelops this quantum critical point. So I've just kind of shown it here. So here's the, say, the ordered phase, and this is the Fermi liquid over here. Then in this region, you get a non-Fermi liquid or a strange metal, sometimes so-called. And then you can often find superconductivity or some other exotic phase that occurs in this region and kind of protects the quantum critical point and removes some of the entropy, or at least that's the way I look at it. And so in the Fermi liquid, you get these usual Fermi liquid properties at low temperatures and the resistivity, specific heat, and susceptibility, temperature dependencies, I should say. And then for non-Fermi liquids, you find that the resistivity can have exponents ranging from 0.5 to 1.5, roughly speaking, but usually they're close to 1. And then C over T usually diverges logarithmically. And susceptibility is a little bit more difficult to interpret, but one finds various non-Curie-like forms. All right, but anyway, this is relevant to what I want to tell you now, because this is work done. There are a number of papers reporting this, but I think the first one was in 2003. And these are high field measurements on uranium, ruthenium-2, silicon-2. This is resistivity versus field at high fields in this range right here. And so basically they find, these curves at say 12 and 10 Kelvin. But then as you lower the temperature, these curves develop some remarkable features. And then from these features, you can pick off certain temperatures and fields from which they could deduce a rather complex phase diagram in the vicinity of what appears to be a quantum critical point. I'll come back to that in a moment. So this is very complicated, I realize, but at any rate, you get all these phase boundaries and phases, and it turns out that in this region, in these phases, the exponent of the resistivity is 1.5 or less. So these are all non-Fermi liquid-like phases. And then in this region, this is more like a Fermi liquid. The resistivity has this exponent of 2. Okay, so these are exotic phases, and I think in the next figure you can see this a little bit more clearly. So this is an easier to understand phase diagram in terms of the various features that was, I think, constructed by Marcelo Jaime. But basically what I just showed you looks like this. And so there's superconductivity down here. This is a hidden order phase. And this is, I think, associated with the peak in the resistivity. So you have itinerant F electrons in this region, non-Fermi liquid in this region, Fermi liquid over here. This is a metamagnetic transition that occurs here. And then you get these different interesting phases. And one of these phases actually turns out to be associated with the formation of a spin density wave, which is shown schematically here. that's based on NMR and neutron scattering measurements. And I don't think all these other phase boundaries have been, I don't think this is understood in detail, but certainly there's a spin density wave in here. There's hidden order in this region right here. And then polarized paramagnetism in this region right here. Okay, now we've wanted to do this in the system we're working on by looking at various iron concentrations and then doing similar measurements. And so I know this is very complex, but basically these are our data like I showed you for the pure compound. And this is the pure compound here. And then these are successively larger amounts of iron. And so this is all in the hidden order regime here. And then over here, you get into the antiferromagnetic region. And then these are the features similar to what I showed you right here. But anyway, if you take these features and you pick out the relevant temperatures and fields, you can make it look a little bit more appealing because you now have basically phase boundaries. So this is the hidden order phase boundary. This is a phase that occurs in the hidden order regime where it's believed there's some Fermi surface reconstruction. This is this exotic phase, which envelops a quantum critical point that's believed to be in this region right here. And so this is where you have the itinerant, highly coherent region over here, the heavy fermion state, if you like. And then you get non-Fermi liquid behavior in this region. And over here, you get a Fermi liquid. So then you can anyway see how these evolve. And so you see that there are features, the hidden order transition temperature is changing, the critical field for the destruction of the hidden order is changing, and these features are moving around a little bit, but they're basically the same until you get to this region where the antiferromagnetism cuts in. And so you can see this more clearly at higher concentrations. So here is antiferromagnetism in this region, hidden order over here. And then again, this is the line delineating the coherent region over here in the non-Fermi liquid region, and then the Fermi liquid over here, and so on and so forth until at some point you only find the antiferromagnetism. So that's basically the way it looks like. So there was some simplification of the previous data I showed you to get to these data, but you can simplify this a little further if you now make, whoops, I'm going to skip this one. Now make this phase diagram where you have temperature versus iron composition and field. And so here, if I look at this plane right here, I'm increasing the magnetic field and I'm suppressing the hidden order in the pure compound. And then there's this phase that has a spin density wave. This is the new phase that I mentioned that's due to this restructuring of the Fermi surface, or that's what's believed. And then this is where it crosses over into a Fermi liquid on this side right here. And then over here, you see the large moment antiferromagnetism. And so it, cuts off the hidden order in here, but then the hidden order reemerges, as you go to higher fields like this, okay? So it's a very interesting and complex phase diagram showing the interrelation of all these different phases that are driven, in this case, by the substitution of iron, that's the iron composition, and the magnetic field in these high field studies. Okay, so anyway, I see that I'm running out of time here, but let me now just come back to the inelastic neutron scattering. So this was work, again, done by Nick Butch and others. And so these are measurements of various iron concentrations, inelastic neutron scattering. So basically you see the incommensurate excitations, and the gap in the hidden order range is 4 MeV, if you can remember back to the earlier slide. And then in the antiferromagnetic regime, it jumps up to about 8 MeV. So these two are in the hidden order range. These are the excitations, these red regions in here. And then when you get into the antiferromagnetic phase, the intensity is much less, but you can see the excitations up here that are around 8 MeV. And then for the commensurate excitation, it happens at about 1.5 MeV in the hidden order range. But then when you get into the antiferromagnetic range, remember it has the period doubling along the z-axis. And even though we don't know what it's due to, it then basically becomes the antiferromagnetic order when you get into the antiferromagnetically ordered phase, and the excitations just disappear because you have this long range antiferromagnetic order. And then this also has been seen under pressure. This is work by Ruthenium and co-workers. And so they did measurements under pressure. And so here you see the contributions from the incommensurate excitations. As I said, at around 4 MeV, then it jumps up to somewhere in the neighborhood of 8 MeV. And then for the commensurate one, around 1.5 or so. And then it disappears when you go into the ordered regime right here. Okay. All right, so let me now come, I think I want to come back to the case of osmium, which I mentioned earlier. So again, this is this part of the periodic table I mentioned where we're doing substitutions for ruthenium. So these are the substitutions that generate holes. These are the ones that generate electrons. And then iron and osmium are isoelectronic. Iron decreases the unit cell volume, osmium increases it. So we found that, that one way we could interpret it early on was that the iron substitutions gave rise to a positive chemical pressure. And so then we observed that the hidden order temperature increases as you go through the transition, similar to what happens under pressure. And now if we were simply to assume that osmium would generate a negative chemical pressure, we would then expect that T0 decreases with osmium concentration. And when we did the osmium substitutions later, these are polycrystalline data. So this is for iron substitution. These are little, disregard these are small features that you see for the polycrystalline samples, and they're just spurious features and you can disregard them. These are the actual phase transitions, which we measured, in detail, just like the data I showed you for the single crystals. So these are the real phase transitions occur along this region for iron. But then if you go in this direction, this is for osmium substitution, you see a very similar thing, that rather than decreasing, this phase transition increases as you add osmium. And there's also a kink in this phase boundary at about 0.1. So you have similar behavior for the osmium substitution as you do for the iron. So since it is, you could associate it with a negative chemical pressure, then this indicates something else must be going on. And so one thing would be a larger spatial extent of the 5d orbital for osmium, or increase of the spin-orbit interaction. And indeed, both of those contributions, could account for this behavior, and the actual chemical pressure is really a minor contribution that's dominated by these other factors. So here's some high pressure data for osmium substitution, similar to what I showed you before. And these are data on the polycrystalline samples, and they differ from the data on the single crystal samples. These materials are harder to deal with, but these concentrations have been independently measured by EDX measurements. So we believe this is what the phase boundary actually looks like. So this is paramagnetic, hidden order, and then the large moment antiferromagnetic regime. And then if you do the same kind of high pressure measurements, you get data similar to what I showed you before. You can pick out the relevant temperatures and pressures. And then for osmium, you find kinks in the phase boundaries. So this is pure uranium, ruthenium 2, silicon 2. And then when you put in some osmium, the kink occurs at lower pressure. And that just evolves as you add more and more osmium. So again, you generate a plane of osmium composition and pressure within which the hidden order phase occurs. And then outside of it, you get a large moment antiferromagnetic phase. Okay, so again, you get this additivity of the tuning parameters of pressure and osmium concentration when you tune the transition using these two mechanisms. Okay, so Peter Riceborough did some calculations, and basically, based on what he did, we would conclude, as I mentioned in the beginning, that really the iron and osmium have stronger hybridization with respect to the 5F states of uranium, and ruthenium is suppressed. And so this then we believe is the real mechanism that is driving this transition. I mean, it is of course due to hybridization, but it doesn't appear to be traceable strongly to the positive or negative chemical pressures. You know, of course they contribute something, but the dominant mechanism appears to be the simple replacement of these atoms with stronger hybridization for ruthenium when you make these two substitutions. And these are just some comments about the calculations of the hybridization energies. They depend upon the matrix element, you know, associated with the electronic orbitals due to uranium and these transition metals that are relevant. And then there's also a binding energy that appears in the denominator. And it turns out that these binding energies are lower for ruthenium due to its electronic structure. And so this then gives rise to a reduction of this hybridization energy relative to iron and osmium. And so as you substitute them in for ruthenium, this then increases the hybridization. And so that they behave similarly in driving the transition from the hidden order phase to the large moment antiferromagnetic phase. All right, so I'm basically at the end. I just want to show you two view graphs from the work of Sean Kung and coworkers. This is Gersh Bloomberg's group. So this is the chirality density interpretation. So basically, what they found from the polarized Raman measurements is that they're believed to be two low-lying singlets in the crystal field electron energy levels, and these have A1G and A2G symmetry. The A1 symmetry is symmetric with respect to vertical and diagonal reflections, as shown here. These are the orbitals for this higher energy singlet. This is the ground state singlet. And then they're antisymmetric for the ground state one. And basically what the evidence, what the experiments and the theoretical interpretation give you is that you can form out of these two wave functions some new wave functions that are believed to be associated with the hidden order phase that have opposite chirality. And so as you go along the c-axis, then you double the length of the unit cell, because this layer has, say, left-hand chirality, this one right-hand chirality, this left-hand, and so on, to generate this kind of a picture. And so this, they believe, is a candidate for this hidden order state. And then they've also looked at the iron substituted materials that we prepared. And so there's an energy associated with the formation of this ground state, or this chirality density wave ground state candidate for hidden order. And so this occurs at about 1.5 millivolts for the pure compound. And then as you add iron, this thing decreases and vanishes in the neighborhood of where the transition was supposed to occur. And then it reemerges on this side. And that's shown in these data right here. These are the low temperature Raman response in the A to G symmetry channel. And then finally, the interpretation is that in the hidden order phase, you get the superposition of these two wave functions, or these two singlets, that give rise to this chirality density wave. But in the antiferromagnetic phase, you can use the same set of wave functions and then generate an antiferromagnetic structure that also has a period doubled along the z-axis. And so here you see the magnetic moments, orbital moments, that are presumably associated with this ordered phase. So this is, I think, one of the more interesting candidates for hidden order. Now, whether it's true or not, I don't know, but it's based upon this hexadecapolar model that Christian Halla and Gabby Cotliar proposed. And I think it's one of the more interesting of the models that have been suggested for hidden order. Okay, so anyway, there's a delicate interplay of competing reactions in this compound give rise to this wide variety of correlated electron phases and phenomena. And I've talked about most of these. And you can tune these competing interactions with pressure, magnetic field, and composition, generate very complex phase diagrams. And substitution of iron or osmium would probably seem to be not very fruitful at the outset, because it's an isoelectronic substitution, but it's similar to applying pressure. And also it gives you some insight, into the mechanism that's driving the transition for the reasons that I've tried to discuss. And so the other thing is that by being able to do this substitution, this isoelectronic substitution, and drive this transition at atmospheric pressure and do this in single crystals, then you do have the opportunity to apply some of the especially spectroscopic types of experiments or techniques to studying hidden order and in this material. And so I've shown you some examples here. And so maybe at some point, these types of experiments will unmask the identity of this mysterious hidden order phase that has eluded researchers for more than 3 decades. So I think this is I'll stop here. This is my group in spring of 2017. My group is much smaller now because a lot of these people have graduated and gone on to other places. And this is the Mayor Hall Breezeway, a picture by Ansel Adams, right around the time UCSD started in 1960. Okay, so anyway, that's thank you for listening and your patience. I hope I've told you a little bit about the interesting and challenging issues that are involved in this problem. And I think this is going to take some time to solve, and so that many of us will be working on this for some time to come in the future. All right, thank you very much.
Thank you, Brian, for a really interesting talk. It's an impressive number of really elegant measurements. So thanks for the review. The most recent ones are particularly interesting. So questions or comments for Brian, just use the chat or raise your hand or unmute yourself.
I have a silly question just to start the conversation. Can I go ahead?
Go ahead, Urshan.
This is Arjanath. What is the philosophical reason you call this phase hidden phase?
Well, I didn't coin that phrase myself. I guess it's really only hidden because it's remained unidentified. It's been really difficult to identify. And I think it's fair to say that there's no consensus that any of these things I've mentioned is, the definitive answer. So that's basically why I think it's called hidden order. And in the beginning, in our experiments in the beginning, it has all the earmarks of a charge or spin density wave. So we thought it was one or the other. And, there are some magnetic excitation, there's some magnetic order, but that's been discounted as being a parasitic type of magnetic order, as I mentioned. So I guess I do believe there's a density wave in there. And so that's one of the reasons why I kind of like this chirality density wave interpretation, as complicated as it is.
Thank you.
So is that going to be a regime where one would look for topological superconductivity? Because you mentioned that at the outset as being.
Well, I mean, that is true. I mean, this compound is a candidate for topological superconductivity. And certainly, there are a lot of interacting order parameters here, and a lot of, giving rise to a very complex and exotic superconducting phase, and it is believed to be a candidate. Now, I don't know if you can predict that a priori, but that's certainly. I would think if you could find other systems that exhibited this behavior, it might be a fruitful place to look.
Maybe then to follow up, and also given the question about chemical pressure, which I think you've explained well with the Osmium study, is there any benefit to looking at combined high magnetic field and pressure studies? Because that was one combination of variables.
Yes, I didn't have time to talk about that, but Dai Aoki has done this under pressure, and it turns out that phase diagram I showed you for a field iron composition and temperature, it looks very similar to what Aoki found when he just did the pure compound under pressure. I mean, all those features are there. I don't know if I have this here. Maybe let me just look quickly. I don't know. Oh, there it is. Okay. So anyway, this is the phase diagram, three-dimensional phase diagram I showed you. And then this is the one that Aoki deduced just from having pressure here. So pressure is like iron concentration. And so the colors are a little different. But anyway, here's hidden order in here, and then antiferromagnetism in here. And he hasn't looked at these other features.
Is this inferred from the iron substitution, or is it a direct measurement of combined pressure and magnetic field?
Oh, this was done using data very similar to what I showed you, except instead of having different iron concentrations, these were done at different pressures.
Yeah, I see. Okay, thanks.
I think that is what these dotted lines refer to, probably the different pressures. But sure, you could imagine, well, it would be very complex, that's for sure. And it takes a while to do these measurements.
More questions or comments? Oh, Brent, go ahead.
It's also, thank you, Russ, and thank you, Brian, for this very interesting and extensive talk, and a lot of data here. I'm thinking about this chemical substitution and the effect of chemical pressure for the iron and osmium substitutions for the ruthenium, where you have a different average change in the unit cell parameter with the different substitutions, which would seem to rule out parallel to pressure. But one of the things that would be similar at these low concentrations of solutes is that you'll have some unit cells that are off the average lattice parameter and some of them that are closer to the lattice parameter. And so there may be a distribution of strains effectively, and some of the phases may be more or less sensitive to the strain distribution. Does that sound at all plausible? I'd have to go back and look at a lot of things to make sense of it.
No, I think that's a very logical way of thinking about it. I mean, what I was talking about is in a very global, macroscopic sense. And but I think if you looked at this in detail, and if you did, low pressure studies and really looked into this issue, I think you would find basically just what you suggest.
Yeah, so some of the coherence that might require good periodicity over several unit cells may be altered differently in affecting the stability of different phases is what I'm thinking if you have heterogeneity in the structure a little bit. But anyway, just a thought.
More questions or comments? Okay, if not, thank you, Brian, for a very comprehensive talk. Very nicely put together.
Okay, well, thank you very much. It was nice to talk with all of you.
Okay, great. And thank you all for joining us.
Thanks, Brian.
Bye-bye.